Welcome to Everything STEAM. I'm your host, Sam Stanford. As a physicist and structural engineer with Jacobs Engineering, I've made many connections with some bright individuals who are either working, studying, or self-taught and passionate about our particular topics of discussion. Today's episode is very exciting to me because it is filled with exhilarating topics like history, mathematics like geometry, both quantum and classical physics, dimensions higher than 3, and of course, the universe. And just a quick heads up, get ready to learn about the geometry of space-time around a black hole, or strings, and even soup cans? Well, kinda. All of this, minus the history part, is entangled with what my guest does for a living. So with that being said, I think it's time for you to meet Dr. Blitz. Blitz received his doctorate in physics in 2022 and is now currently working as a postdoctoral researcher in a mathematics department in Central Europe. While his degree is in physics, his doctoral advisor was working as a mathematician, even though he too has a PhD in physics. But much of Blitz's work has been mathematical in nature and inspired from physics problems, but he still works in true physics. His current research is in differential geometry, or math, and general relativity, physics, which fortunately are very closely related. But outside of all of this, in his free time, he plays video games, Dungeons and Dragons, and makes science and political content on TikTok. So if you're interested in that, just give Dr. Blitz a search on TikTok to connect. So, now that you've been introduced to Dr. Blitz and the topic of this podcast, we're going to head into the first segment where we plan to talk about the fine line between math and physics. Cheers. Hey, Dr. Blitz, or Blitz, if you want to be called Blitz for short. How are you doing, man? Glad to have you on the podcast.
Thanks for having me. Yeah, no, I'm doing all right.
Awesome. Again, you're just cool with going with Blitz.
Yeah, I go by that. I've gone by that since summer camp, I suppose.
First of all, not to geek out or anything, but I'm really excited about the things that we're going to be talking about tonight within segments 1 to 3. It's from a fanboy perspective, obviously. Like, what you're doing is really, really interesting. For segment 1, we wanted to start out with kind of a story aspect to the podcast, and also paint a bit of a picture for what Blitz actually does, which is mathematical physics. So without further ado, I want to pose the question, or maybe start the discussion on the blurry line of mathematical physics. Do you want to take it away from there?
So the story is that there was a time 400 years ago where science was really just about doing experiments and then seeing what happens, and sometimes finding patterns. Maybe you write down some numbers and see that it's a line, but just finding patterns and then making predictions. But sometime around, say, 350 years ago with Newton, you had formal mathematics finally coming to the forefront, and you have actual explicit characterizations of relationships. We're talking things like Newton's second law, force equals mass times acceleration. Seems kind of obvious today, maybe not obvious, but at the time it was remarkable. There's just this mathematical relationship between things. And along with that came the development of calculus, which was perhaps the first example of mathematical physics happening, right? Before, it was experimentation and observation and finding relationships. Now you can actually develop mathematics using physics, or vice versa. So if we have to talk about what mathematical physics is, you might call it the thing that straddles the line between pure maths and pure physics, right? So there's interplay between the two. You have mathematicians. These are people like David Hilbert, people like Emmy Noether, who were basically just mathematicians. And their contributions in mathematics led to developments in physics. And they wrote several papers in physics and so on and so forth. And then you have physicists. These are people like Newton, Einstein, Paul Dirac, Ed Witten, to name a few, who revolutionized areas of mathematics using physical intuition. So the whole point of mathematical physics, and the reason why I found myself here, is because there's a lot of structure. There's a lot of rules in mathematics, right? That makes things more rigid, more concrete. And then in physics, you have like this intuition, this kind of like almost loosey-goosey, fly by the seat of your pants type intuition. And, some people are really good at one, some people are really good at the other. I would say maybe I'm half and half. So you end up halfway between a mathematical physics.
Okay, that makes a lot of sense. And I mean, before not to jump back too far, but like with Newton, he developed, well, he's not like the one to develop calculus. There was people that were working in
Leibniz
tandem.
too.
Yeah, it's just politics at that point. But before that, I mean, the largest foundations of mathematics were Euclidean geometry and algebra, right?
Yep.
So this is kind of like getting into the weeds of how we can study change over time. So it's like like you said, a more representation of reality, and that's where we could actually start doing some real physics with mathematics.
Yeah, and this happens a lot, right? You have something in physics that you have to represent, and the tools don't exist. So you either invent them yourself, or you go ask your mathematician buddy to do it for you.
Yeah, makes sense. So give me some examples where we go from physics to mathematics. I know you dropped a couple names, and one of them was Ed Witten. Do you want to run me through a quick story about Ed Witten?
Yeah, so I don't know a story. He's actually I've seen him in person once. He's a very quiet person. I never even got the chance to talk to him. But so I don't know how much of a story there is, but he's somewhat famous because of his work that he did in the 80s and 90s. And obviously he continues to do great work. He's still alive, by the way. But he's the only physicist to ever win the Fields Medal, which the Fields Medal, for those who don't know, is the Nobel Prize of mathematics. There isn't a Nobel Prize in math. The Fields Medal is like that, with one stipulation: you can only win it if you're younger than 40. So it's like highly prestigious. Some would say that the Abel Prize is the Nobel Prize of math. It doesn't matter. But anyway, he won the Fields Medal and is the only physicist to have done so. And part of the reason why he won this award is because he was working on some stuff in like topological quantum field theory, which I'm not even going to bother going into, but it's a physics thing. It's a very like abstract physics thing. Has relationships with like string theory and quantum gravity and all of that. And using that physical intuition that he developed about like this type of theory called Chern-Simons theory, he actually proved some completely unrelated results in knot theory. Like not the theory of like the mathematical theory of knots. This is like how things can intertwine with each other. I don't know anything about knot theory, but it's one of those things where you take physics and then you just get something completely remarkable and unrelated out of it. So, I mean, Ed Witten's like, he's crazy smart. I hope I get the chance to actually sit down and have a conversation with him at some point.
Yeah, that's really interesting. I maybe from a top level, I'm thinking about like maybe tying knot theory with quantum field theory. I'm just thinking about how the fields like interact with each other. Maybe that's the bridge across. I'm not sure. So did somebody come across what his work was and was like, I'm working on knot theory. I feel like this, like the principles that he's using could actually apply here. Is that kind of how that happened?
So I suspect it's even more impressive that he just knew about knot theory when he was working on his topological quantum field theory stuff. And he's like, hey, I have this result. I'm going to prove this other thing. The man is brilliant. I suspect he just knew. I don't think that he got help. I'm sure he had like some sort of collaboration, but yeah.
He was probably he wasn't the lone wolf, but he definitely takes the credit. Yeah, that makes a lot of sense. So that's really an example of going from physics to mathematics, I guess, if you want to categorize it that way. But what if we flip it like 180 and we go from mathematics to physics? What is a good example of that?
So here you arguably have a lot more examples, if only because the period of time in the late 1800s, the early 1900s, there was a lot of mathematics that was happening at the time, like a lot of very high-level mathematics. This is when kind of modern mathematics was born, really. And this is also the same time when quantum mechanics, general relativity, these things were being developed. So you have a whole bunch of these people. Hilbert is a great example. Hilbert was a mathematician, but there's this thing in physics called the Einstein-Hilbert action, which is kind of a compact way of describing general relativity. And it was a collaboration between Einstein, obviously a physicist, and Hilbert, a mathematician, that came up with this like beautiful description of general relativity. Another, and this is arguably my favorite example, is Emmy Noether. She's German. You have to pronounce the O with an umlaut, right? She's was once described as the greatest female mathematician of all time. like brilliant woman, and also very, very challenging to be a female mathematician in the 1800s, late 1800s, early 1900s, right?
Yeah.
But so she did a lot of work. She was genuinely a mathematician. She worked with mathematicians. But one of the things that popped out of her work was something called, well, it's called Noether's theorem. At least that's what it's called in physics. There's 3 Noether's theorems, but you know. Yeah. The one that physicists care about is the one that gives mathematical grounding to every conservation law. So energy conservation, mathematically proven by Emmy Noether. Angular momentum, momentum conservation, all of these things, charge conservation, all of these things are just mathematical consequences of Noether's theorem, which is remarkable. And it's why she's like, it is that single result alone that explains why if you go to her Wikipedia page, it says that she's a mathematical physicist, because she basically gave a grounding for these otherwise mysterious things, right? Like, why would energy be conserved? It just is? No, there's a deeper reason, and she explained that. So it's this kind of thing where you just and she was doing some really abstract stuff with like functional calculus and calculus of variations, and this kind of just happened. So this is the kind of thing that does happen perhaps more often, at least in around the turn of the 20th century. Perhaps maybe not anymore, just because there's more communication between math and physics people anyway. So there's less like people who are doing just math that accidentally do a physics thing, right?
Yeah, no, that makes sense. I mean, yeah, it has to happen interchangeably. It's just really cool whenever one happens with the other and vice versa. But yeah, it happens all the time. We could literally sit here and just talk about countless examples if we really wanted to. But yeah, I honestly, so I'm not too keen on a lot of the history in physics, and whenever you said Emmy Noether, I actually didn't know about her until we met. So yeah. I mean, that's fantastic to hear. Obviously someone that overcame some really interesting sociological odds to be considered like the best in that realm, and give us. Oh, go ahead. Sorry.
Oh, no. I was going to say also, funny story. It wasn't, she was just a woman doing math. She was also Jewish, working in Germany, and didn't leave until 1933. So she had quite a struggle ahead of her.
Wow. That's okay. That's even, I don't even know how you could get even more next level, but it just happened.
Yep.
That's super impressive. Jeez. And then, I mean, also then to contribute to like the most fundamental laws that we have, right? Because we use energy and momentum conservation laws in anything from classical physics dealing with relativity all the way to particle physics. So it's
literally like, everything.
It literally is. That's amazing. Arguably, I mean, if you wanted to argue, she's on a list of like the most influential people in physics.
Oh yeah. When I was I think I first learned about this like maybe first year of grad school, because they don't really talk about Noether's theorems because it's kind of complicated. But I don't know why the message stuck with me, but the fact that it's just a consequence of some somewhat straightforward math that like whoops energy conservation just kind of happens. And you see it in like classical physics, and then you go to your particle physics classes, because this is what you do when you're in grad school for physics. You go to your particle physics classes or whatever, and then it's just like, oh, and then we apply Noether's theorem, and here is a conserved current. So this is like a thing like, oh, charge is conserved, which just kind of happens, just accidentally. So no, it's arguably the most useful tool, one of the most useful tools. Also, by the way, it's useful in mathematics too, because these they're called conserved currents, but they're basically just things that are conserved. If you can find a system that has them, and often there are systems that have them, for like a partial differential equation or something, now solving your equation becomes a lot easier. In just a purely mathematical setting, has nothing to do with physics. So there's a lot of crossover here.
Yeah, I mean, it's extremely elegant. I like to say that like simplicity is bliss sometimes. Like we don't need to stretch for like for example, I mean, if to talk about like quantum mechanics and like the fundamental aspects of quantum mechanics, there's these different hypotheses or how do I want to say like different interpretations of the wave function. Like, for example, like you and I talked offset a little while ago about the many worlds interpretation. And then there's these other interpretations that take the wave function, but have to add hidden variables or have to add certain explanations to create some sort of a more involved result. And why not just stick with the one that is tried and true and more elegant or simplistic?
Well, because arguably it's more radical, right? It's a little bit harder to swallow when you strip everything down to its bare minimum, but it's neither here nor there.
Understood. So one, I guess maybe like if you don't mind, we could go through a couple more examples and then run out of this first segment, because I know we have a lot more to talk about in segment 2 and 3. Is there anything you would you like to maybe converse a little bit about Paul Dirac, or maybe is his name Charles? Is it Charles Schwarzschild?
Carl, maybe?
Is it Carl?
I think he was a German fellow.
I feel like it's Carl.
I'm checking on Wikipedia right now. Carl Schwarzschild. Yeah.
There we go. Yeah.
Shield, I guess, if you want to be.
Yeah, true. But one of the, I think from a story aspect, before we talk about anything that's, I guess, a little more technical, is that he was wasn't he in like World War I?
World War I. He was in the trenches. 1916.
Taking Einstein's, general relativity and being like, you know what? I feel like I can find something out of this.
Yep.
You want to maybe take us through the backstory there and explain like why his mathematical genius developed something in physics? Yeah,
so I don't even know if he counts as a mathematician, but this is one of those examples where, I mean, they were all mathematicians and physicists at the time. Like they were all doing everything.
Yeah.
What a time to be alive, right? But so this guy, and this is the story that I've been told. Fact check me if it's wrong. But this guy, young fellow working in the trenches. I want to say he was probably on the German side, but it was World War I, so they weren't the bad guys yet. Einstein publishes his general relativity in 1915, and then like less than a year later or something like that, in 1916, Schwarzschild writes a letter to Einstein and says, "Hey, here's a solution." So when we're talking about general relativity, this is like it's described by an equation, right? We're talking about Einstein's field equations. It's a set of 10 nonlinear second-order partial differential equations, which is horribly nasty to solve. In fact, it's actually known that there is no general solution. There are very, very specific solutions. But what Schwarzschild did is he came up with, I think, the first exact solution, meaning that it's not like an approximate solution that only works for small values of whatever. This is an exact solution to the Einstein field equations. And what the Einstein field equations describe, by the way, is they describe how space curves in the presence of stuff, or otherwise not. It turns out that the easiest solutions to find are the ones where there's no matter at all. And that's what Schwarzschild did. When there's no matter, you could just have flat space-time. This is very uninteresting. It's just, we call it Minkowski space, another mathematician, by the way, who was involved in this whole story. And you just have very flat, very empty space-time. But that's not the only possible solution. You could have the so-called Schwarzschild solution, which is effectively what we now know as the simplest black hole solution. So you might say, well, the Einstein field equations, there's a left-hand side which tells you the curvature and the right-hand side which tells you the matter, right?
Yep.
And so I told you that Schwarzschild found a solution when there's no matter, when there's no stuff. And you'd say, well, but a black hole has stuff, right? Well, so this is why we might say that all of the stuff at the black hole is in the singularity. That is, if you take that as true, then you can solve the Einstein field equations everywhere outside of that singularity where there is no stuff. And then it's a vacuum solution. But what ends up happening is that just by doing some rather clever mathematics, picking a good choice of coordinates, this is like writing down a so-called ansatz, which is kind of like a guess at a solution, and then just checking that it works, he came up with a solution. And we have black holes to thank for him, or we have him to thank for black holes, right?
Yes. Right.
They weren't discovered until what? Like I think that the first evidence was like in the 80s. So that was 65 or 65-ish years later, that this mathematical curiosity, which people didn't even really take seriously as an actual thing that existed.
Right.
It happened to be discovered in real life as a result of this mathematical calculation that was done. So this is, I mean, it's just like it's one of those things where it's brilliant, but when you're taught it in grad school or when you learn about these things, you see it and you're like, this is so obvious. No wonder he came up with it in like 8 months. but I mean, obviously, like it wasn't obvious at the time. Otherwise, I mean,
Right.
Einstein was clearly brilliant, but he didn't come up with it. So
True. Very true. Very true. I think that's pretty good. I like that. Those are really good examples of how you could go back and forth between mathematics and physics. So I think we're gonna cut it short here on segment one. But then whenever we come back, we're gonna get more into the weeds of what Blitz actually does for. Well, I guess we're gonna set the stage for what he does in his research. So stick around. All right, we're back. This is segment two, and I apologize to Blitz whenever we went into break because I prefaced this next segment and I totally skipped over the fact that we wanted to talk about what mathematical physicists actually do, because I'm sure for the people out there that don't really know much about physics or mathematics, they really have no idea what you do like on a day-to-day. So let's start there. Blitz, what do mathematical physicists do? Give me your rundown.
So it's actually and I can't say this for certain, but I suspect it's basically the same thing that mathematicians do and the same thing that theoretical physicists do. Theoretical physicists are a little bit more physicsy than mathematical physicists, which is, we read papers. I am subscribed to a listserv, so every day I get two emails that say, here are the papers that are put on the preprint server today. Most of the time I just read the titles, and if it's interesting, I'll read the abstract, and if it's really interesting, I'll read the paper. Maybe that takes up half an hour of my day, depending on if the papers are interesting. So I spend some time reading. I have a few projects that are currently ongoing. These are things that I'm working on, either writing a paper for or what have you. So often after I start my day and, I go through my emails, it's a matter of picking a project that I want to work on and working on it. Now, to me, that looks like most of the time sitting at my desk in my home office. Sometimes I'm on campus, and scribbling on a piece of paper, or sometimes scribbling in a notepad file where I have some computer algebra software that I can use to do these calculations a little bit more efficiently. And it can be kind of grindy, but I put on a YouTube video, put on some music, and it just is what it is. Sometimes though, and so that is where I'm at my happiest, if you will. When I have a direction to go, when I have something to be doing, when there's just a calculation that I need to do. In fact, this is how I spent the last 2 days, or I suppose I spent today and I spent Friday working on a calculation. I knew how to do it. I just had to get it done. And it's, relaxing in a sense, I guess, because it's very structured and you know where you're going. You know what the answer should be, or roughly anyway, and you just make your way from A to B. So that's when I'm at my most happiest. And if I spend a day doing that, I'm in a good mood. Least happiest is when there's a calculation to do and I don't know how to do it, or there's something I don't understand and I need to find out how to understand it. That happens quite a lot. I just turned 30, so I'm still quite young in my career, early in my career. I don't know a lot of things. I mean, compared to my colleagues, I'm just a baby. So this is to say, if I don't know something, a relatively straightforward thing, I have to go find a textbook, or I go find a pedagogical overview or pedagogical literature review or something like that on the preprint server, and I just sit and read. And this is one of the things that they actually don't teach you about what it's like to be an academic researcher. Is it's not about knowing everything, right? It's about knowing how to teach yourself something in a short enough time that you can use it for your work. Because if we were on a semester system in college or in grad school or whatever, you spend 4 hours learning the basics of a subject 4 months learning the basics of a subject. If that is what I had to do every time I had to familiarize myself with something that I needed, I would never publish a paper, right? So the most recent example of this is that I was working on a project that I'm working on with my supervisor here in Europe, and we were kind of stuck on a particular part of a problem that we were working on. We had a differential equation that we didn't know how to solve. We didn't even know if it had solutions or if those solutions were unique. We basically met twice a week for 2 hours, at 2 hours every meeting, for 3 weeks, staring at a differential equation, not making any progress. It was really rough, and it's one of those times where it's like, well, maybe this is the end of my career, right? But then miracle happened. I did some digging. I branched out, used my physics chops. My supervisor is a mathematician, like a pure mathematician here. I said, well, I'm not finding any answers to this question in the physics literature. Let's go check in the math literature. Let's go check the physics literature. Did some checking, found some papers from the 70s and 80s, because it's always the 70s and 80s, and they're always like Russians who solve these problems, right? That's a whole separate story, and we can go into that later if you want. But I found some old papers that were like, oh hey, here's a solution. In fact, I spent a week tracking down various citations, reading the papers that those papers reference, reading some follow-up papers and so on. And I learned a little bit about what you might call, jargon alert, non-abelian gauge theory. And I found that there is, this is not stuff that I know. I didn't learn it in grad school. It's not really something that would be taught in grad school, but I learned about it and then I could apply it to this problem. So, that week was kind of rough because I spent a week just reading and occasionally doing a calculation to make sure I understood what I was doing. So I mean, those are the two biggest things that I do: reading and calculating. Sometimes I'll have a result, and I finished calculating, I finished reading, and now I have to write it, right? Maybe about a quarter of the time in a given week I spend writing, and this is just writing up a manuscript to be submitted to a journal. One of the ways that I like to keep notes, because I'm very disorganized with physical paper, is even if I'm not like writing up like a formal paper, I'll still sketch out the ideas in the form of a manuscript that I would submit. And then once everything is done, once all the ideas are there, then I can go back, clean it up, and actually submit it. But that's the basic division of time. Reading and calculating take up the most of it, and also meetings, I suppose, meeting with various collaborators, thinking about ideas.
Yeah, makes sense. I have two questions, just for people listening, because you started out saying that you have these calculations that you know the answer to, meaning, and please correct me if I'm wrong, meaning that you kind of know the nature of the answer, but the parameters that you input are different from, obviously you don't know the exact answer, but
otherwise I wouldn't be calculating.
Yeah, yeah, exactly. I just wanted to make that clear. And secondly, like, whenever you're publishing these papers, who are you publishing to, and who's reviewing your work?
So I mean, it depends. So I mean, I'm still early in my career. I have 3 papers accepted, 1 paper that's still under review, another paper that is nearly done, which we've been saying it's been nearly done for a year, but we just keep finding more and more things to add to it. Not that we keep finding problems. So far, everything everything that I've done has been published or submitted to. Well, everything that I've published has been published in a mathematics journal. So if people ask me what my specialty is, I often say something like differential geometry and general relativity. So these two things are basically the same thing. What Einstein did is he basically took the known general relativity of the late 1800s. Sorry, he took the known differential geometry of the late 1800s and then just said, well, what if this was a physics law? And then that was the whole thing, right? So the journals that I'm submitting to are differential geometry journals primarily. And I mean, I am going to be submitted. I have 1 paper that's submitted to a physics journal now, but we'll see if it gets accepted. Another project I'm working on is also going to be submitted to a physics journal. But for the most part, what happens during the review process, and I've been a reviewer for several papers, like for 4 or 5 papers at this point, what happens is basically you submit it to the editor. The editor is usually like the dean of some math department or something like that at some university, maybe at Indiana or maybe in Tokyo or whatever. And then they say, well, I don't know anything about this, but I know somebody who does. So they send it off to somebody who does know something about it. And then that person says, well, I'm really busy. And I don't know anything about this very specific thing that this person's writing about, but I know kind of like the general story. So I'm going to send this to 2 or 3 people in the math community, in the physics community, whatever, who are experts enough in this very niche subfield of mathematics or physics that they can actually evaluate the work. So it's just, and usually these are going to be rarely grad students. There'll be postdocs like myself, there'll be professors, and then it gets read by those people. And if they like it, they'll say, you're good to go. And if they don't like it, they'll say, try again somewhere else.
Understand. So that's kind of the basics of peer review in that aspect. But yeah, it's limited. It seems like it's limited peer review. You only get like a few different people that could actually look at your stuff.
So I've made this comment before. It can be kind of incestuous almost. Like and I mean that in like the least naughty way, right?
Yeah.
That as an example, there's this paper that I submitted in I don't know, like November of 2021 or something like that, which was accepted. And but about a week before we submitted, there was another paper that was released by a guy, I'm not going to name names, by another guy who basically had very similar results from us. We were working completely independently. And so we both submitted our results basically at the same time. I mean, like, we did it in completely different ways. We came up with like different generalizations, but the core ideas were basically the same. And so we both submitted our papers. And I don't know, because this is anonymous, by the way, this whole peer review like process is anonymous for good reason.
Yeah,
I don't know who reviewed our paper, but I suspect it was him. Because you know, so they'll review it, and if it's good enough that they want to accept it, there's just some changes that have to be made. They'll be like, hey, you forgot to cite this person here because there's this person in the literature who did this thing, or hey, you know, you didn't mention this result from wherever. And the reason I suspect it was him is because whoever our reviewer was said, hey, you forgot to cite this paper, and this paper, who all happen to be by that same guy, which happens a lot. And then the funniest thing is, when he submitted his paper, I was asked to review it. So I did. And I said, hey, you're missing this result from my paper. This result follows from that result. So like, the thing is there are maybe 24, maybe not even 24, maybe a dozen people in the world who do the thing that I do. And this is not to say because it's so hard that only I could do it, but it's just because there's so much math out there. There's so much physics out there that, you know, I've heard the number, and I could be way off, but I've heard the number that there are 10,000 physicists in the world, like professional working physicists, and maybe about the same amount of mathematicians. And keep in mind, these physicists are condensed matter, they're experimentalists, they're particle physicists. The mathematicians are, you know, number theorists and, you know, analysts. And so, you know, the intersection between these areas, the numbers get smaller and smaller. So you just end up with, you know, a few people who can read a paper. And I mean, mostly that's good enough, right? Because it's competitive. So if somebody saw a paper that, you know, like if they're in your area and they think that your work is bad, they will tell you. Yeah. So it's not like, it would be one thing if we were all working in the same group, but we're not.
Right. That is true. The competitive nature does make it a better peer review process, I think. That does make a lot of sense, because we usually think about peer review like in terms of numbers, but when you boil it down, it's not a numbers game.
You just when we talk about peer review, even in like experimental physics, it's like they send it out, well, for very, very large projects like the ones at CERN, I'm sure they have hundreds or like dozens or hundreds of people reviewing. But like for most physics papers, most papers in general, at least in the physics and math communities, it's like the expected number is 2 or 3 reviewers, and then it gets published. And the point is that like the people doing the reviewing are expected to be able to be objective and be reasonable. And the other thing is that, at least, and here is a difference between what I do and what, you know, like experimental physicists do. They're not checking methodology in what I do, right? There's no like data. They don't have to like make sure that your experiments were unbiased, or that like you accounted for this systematic error or whatever, or that, you know, that your data wasn't made up or whatever. It's basically mathematical proofs and like, you know, checking that claims, like if you're making a claim that it can be observed or that it agrees with the data or whatever, they're just checking those things. So it is easier to peer review, I imagine, because it's you're not working with like data and experimental procedure.
Yeah, that makes sense. That's cool. No, I mean, I think that's really valuable of talking about like the peer review process and difference between mathematical and experimental. So that's really, I like that. So sorry, we kind of got off topic a little bit.
Sorry about that.
No, it was my question. So.
We can still talk about the Russians, by the way.
I think we should, because why not? Please.
Okay. Yeah. Okay. So there's a joke, and I actually so there's kind of like this ongoing thing, right? So Russians are really, at least historically, very, very good mathematicians, very, very good physicists. Like they had a different way of teaching over there, especially during the Soviet era. And so there was this kind of like ongoing thing where there's the Soviet bloc where they have all of their mathematicians and physicists doing their own thing and they're publishing in Russian. And then there was everybody else who's, at least after about the 1930s or so, publishing in English. Everybody else in the world, in Japan and France and Germany and the United States, everybody's publishing in English. So there's not really a whole lot of crosstalk either, because, you know, there's Soviets and then there's non-Soviets, and so like there's politics involved, of course.
Yeah.
And it's not like that you would submit your journal to your English paper to a Russian journal, and a Russian physicist or a Russian mathematician who only speaks Russian wouldn't submit their paper to an English speaking journal. So there wasn't a lot of crossover. You have to remember that before the 1990s, even these journals were physical pieces of paper, and so there was an iron curtain up, right? This means that if you wanted to get the journals, like even if you spoke Russian and you wanted to read the Russian journal, you had to find somebody from the USSR who could give you it. Because it's just how else were you supposed to get it, right? So what ended up happening is you have a whole bunch of known results in the English speaking community. It's kind of like the lore of the physics and math community where these are known results, and then there's some open questions that haven't been solved. There's some problems that are active areas of research. But then lo and behold, and this happens to this day. There's still some active areas of research, open problems. And then it turns out that had you been omniscient and been able to read the Russian papers and the English papers, turns out that the Russians solved the English problem, right?
Mm-hmm.
And so what ends up happening quite a lot, especially after the Soviet Union fell and after the development of the internet and stuff, what ends up happening is that there's so much extra information that just wasn't part of the compendium of known knowledge in math and physics in the English speaking world. And so, in fact, there was even a joke about this on The Big Bang Theory in one of their later episodes where the main character Sheldon and his wife Amy, they have this theory, and then they discover after doing a literature review that there was a Russian who published something about it and proved it wrong in the 1970s. Right. and this isn't even just this isn't even just an American thing. I was talking to my supervisor here, and he said that something that he heard once is the easiest way to get a master's degree in mathematics is to learn Russian and then translate a Russian paper and pass it off as your own. because nobody does that. Nobody has the results. And so luckily enough, the result that I needed for this project I was working on, it was published by a Russian a Russian physicist, actually. But I only found out about it because I was asking people, and my former supervisor happened to know about it. He happened to know about this obscure Russian result, which, since then, since the last 30 years or so, actually isn't so obscure anymore because it's remarkably useful. But it is one of these things where it wasn't really talked about in the English-speaking world until the 90s, I guess. So it's just a very strange thing that geopolitics comes into play here.
I mean, it's extremely relevant. It's something that we definitely don't, that most people probably don't think about until they're actually submersed into a situation like yours. That's really cool. I never really even thought about that. That's pretty interesting. And imagine if when the Soviet Union fell and all of this information was lost, that would be unfortunate, extremely unfortunate.
Well, but it wasn't lost, right?
I'm saying if it was.
Oh, yeah. Oh, it'd be like the burning of the Library of Alexandria.
Exactly. That's what I'm.
Yeah, it would have been really bad. But I mean, so I have some people who work here who I'm in the Czech Republic, right? And so the Czech Republic wasn't in the Soviet Union, but it was part of the Eastern Bloc, right? And Austria was not. But where I am is about an hour and a half away from Vienna. And there are people who have been here and for 30, 40 years from before the fall of the Soviet Union and the Eastern Bloc and all that, who have been collaborating with people from Vienna. And so there was crosstalk, but not from the heartland of, the Soviet Union, not from deep in Russia, not from New York. There wasn't, on the borders of the Iron Curtain where things were a little bit, more fluid. You can have there were still, there was some crosstalk because, you don't, the people, it was Czechoslovakia at the time, they didn't speak Russian, they spoke Czech or Slovakian and the Austrians, they spoke German. So there was some crossover, but it was a real thing that happened.
That's crazy. That's really cool. I love that. So to transition a little bit, because I know we wanted to talk about your research. I think it would be good to maybe talk about or define some things or that you deal with in your research. I know that we have here on the list conformal geometry, hypersurfaces, submanifolds, and then of course the holographic principle. So do you want to maybe take these people through a little bit of of a definition before we jump into the exacts of what you do?
Yeah, sure. So, I mean, we may as well start at the top. But we can't even start at conformal geometry because we still have to talk about what non-conformal geometry is, right? Okay. So when you're in like, I don't know when people take geometry anymore. I didn't actually take geometry as a class.
For me, 10th grade, so 9th, 10th grade potentially, and that was only Euclidean.
Let's say high school. Right? When you're learning geometry, you're learning about triangles and angles, and maybe there's some trig involved, so you do sines and cosines and things like that. And you may have even, if you were lucky and had a good teacher, you may have even done some like these kind of 2-column proofs things, right? Where you prove that like I don't know, I can't even think of an example, that 2 triangles are similar if they have the same angles or something like that, right? Mm-hmm. So that is all of that geometry that you do. You never even get into 3-dimensional geometry. It's all like stuff that you can draw on a sheet of paper, right? Triangles, squares, angles, parallel lines, all this lovely stuff. This is standard 2-dimensional Euclidean geometry. When I say Euclidean, named after Euclid, Greek guy, kind of invented geometry, really famous dude, has a book. It was basically the standard of geometry for 2,000 years. Big deal. Haven't read it. I should read it, but big deal. Right. So Euclidean geometry is the geometry of flat things. Now, you can do Euclidean geometry in however many dimensions that you want. You could like regular geometry in 3 dimensions, like think of like cubes and like spheres and pyramids and things like that. This is all Euclidean geometry because things still work out. The main postulate of Euclidean geometry that isn't held up. Okay, let me back up. There are 5 main axioms of Euclidean geometry that Euclid lays out, right? Okay. I don't remember the other 4, but the 5th one's important. The 5th one's really important. The postulate is that parallel lines never meet. It sounds obvious, sounds intuitive. I don't. So I have chopsticks, right? For those who aren't watching, I'm holding up chopsticks. If I just drew these straight lines up, they would just go on forever because we live in a roughly Euclidean universe. Say roughly, we can get into that later if necessary.
Of course. Yeah.
Parallel lines don't meet, but that is an assumption, right? It depends on what we mean by parallel lines. It depends on what we mean by meet. And so if you just relax that assumption, if you just say, well, what if they did? Well, now you get into the realm of non-Euclidean geometry. The other 4 postulates, which I can't remember, I really should know these, still hold. They're things like, a line segment is unique between 2 points or something like that. They're like very basic, like fundamental assumptions about how geometry should work. But if you assume that parallel lines, say, can meet, well, now you can get different types of geometry. So the prototypical example is something like the surface of a sphere. So think about like the Earth, right? The Earth is a globe, as I hope we all know.
Hopefully.
So on the surface of a sphere, what does a straight line look like? Well, it can't be like perfectly straight because it would leave the sphere. So we need a better definition of a straight line. And the definition that we use on the surface of the sphere is something called a great circle. This is basically what would happen if you took the equator or took any lines of, what are the ones that go north to south?
The latitude.
Latitude? Yeah, lines of latitude. And you just like rotated them however which way. Notably, lines of longitude are not great circles, but a great circle is just any circle on the surface of your sphere that has the same radius, right? Yep. And so you could rotate it however which way. We call those straight lines. And the reason they're straight lines is because if you got in a car and you drove along that path, you wouldn't have to turn your wheel at all.
Yeah.
Right. You could just drive along the equator without touching your wheel. You could drive north-south without touching your wheel at all. Notably, though, if you were on, say, the 40th parallel north, and you tried to drive east to west, you would have to turn your wheel left in order to stay on the 40th parallel. You could just kind of think about like what would happen. You're driving along, but you would kind of curve down. Not because of gravity, but just because of the geometry.
Right.
So we have this definition of straight line. Basically, you get in a car, you don't turn your wheel, that's a straight line. And so what happens if you drive on these straight lines on Earth? Well, you start off, let's say you're on the equator. You and your friend are on the equator, you're next to each other, and you're driving in the exact same direction. So if this was Euclidean geometry, you'd just drive in the same direction forever, and you'd never touch. But if you do that on the Earth, you'll drive north from the equator. You drive north. When you get to the North Pole, you'll touch.
Yep.
And so now we have parallel lines that do meet because we defined parallel lines in this new way. There's another notion of a non-Euclidean geometry. We might call it hyperbolic geometry. A little bit harder to visualize. We're thinking about like lines on the surface of a Pringle. So that would be like a 2-dimensional hyperbolic geometry, and it doesn't really matter. But the point is that the notion of straight lines, what it means for a line to be straight, can be like, once we've thrown out that notions, these lines are just like actually perfect straight lines, we can go hog wild with these. We can just like generalize the crap out of it. Am I allowed to say that?
Oh yeah.
Okay.
Yeah, you're good.
We can just do whatever we want. We can call whatever we want a straight line, as long as the rule that we follow is that if you drive along it, you never have to turn your wheel. That is the one rule that we demand. And so, well, what's the difference between, say, the surface of a sphere and a sheet of paper? Well, the surface of a sphere kind of closes in on itself. It's curved.
Yep.
Same with a Pringle. A Pringle is curved, whereas a piece of paper isn't. And as an aside, the reason why you can't make a perfectly proportioned map of the Earth is because a sphere has a different curvature than a sheet of paper. So there's never going to be any way that you can map one into the other without distortion.
Yep.
Right. So now we're in the realm of non-Euclidean geometry. And now we can just ask, well, a sphere is really nice. The notion of a straight line is really easy to visualize. But what if you just had like this horrible lumpy thing? Wasn't a sphere, wasn't a Pringle, wasn't a plane. It just had lumps everywhere. You can imagine straight lines could be like, curving around hills and things like that. Whatever. You could do that. And so when you talk about that, we're talking about Riemannian geometry. This is kind of the generalization of Euclidean geometry, where we're still in the two-dimensional realm, but that's easy for visualization, right? Think about like a topographical map, like a straight line. Maybe the shortest point from A to B isn't to just go straight, because you'd have to like go over a hill or something. Maybe it'd make more sense to go like around, right? And that would be your new straight line. So when we talk about Riemannian geometry, we're just talking about this generalized form where straight lines aren't straight, and as another consequence, triangles don't have 180 degrees on the inside anymore. Also weird. And so we can just study properties of this geometry, and this is useful because there's various like neat theorems about this. Is purely Riemannian geometry. And by the way, if I'm going too long, stop me.
No, this is wonderful.
So in fact, I actually didn't mention it. I do TikTok. I'm a TikTok creator, I guess, which is weird to say. But one of my favorite, one thing that people ask me a lot is, what's your favorite math formula? And my favorite math formula is a very classical formula invented by Gauss, because everything was invented by Gauss, from the 1800s. It's called the Theorema Egregium, which is Latin for the miraculous theorem or the egregious theorem. And in the simplest terms, the Theorema Egregium explains why it's useful to fold a piece of pizza if you don't want it to droop. So when you have a flat piece of pizza, it'll just droop. But if you fold it in half, it doesn't droop, so long as it's not stretchy. And the reason this happens is this is like a Riemannian thing. There's a notion of something called an embedding, which is like a two-dimensional thing in a three-dimensional world. A piece of pizza is kind of two-dimensional. And it basically says if you take the curvature in one direction and multiply it by the curvature in the other direction, it doesn't matter how you put that thing in three-dimensional space, it'll always be the same. So if you take a flat piece of pizza, the curvature in one direction is 0. It's just flat. The curvature in the other direction is 0. It's just flat. So now if you take that piece of pizza and you bend it however you want, as long as you don't stretch it, if you have a curvature in one direction, in order for the product of the two to be 0, the curvature in the other direction has to be 0.
Yeah.
Which means that if you fold a piece of pizza up in like a U shape, then the other direction can't curve at all.
Yep.
And so that's why it can't droop, which is remarkable.
I love that.
It's like it explains why New Yorkers hold the pizza the way they do, right? But anyway, so this is why it's useful to study things like Riemannian geometry, because you can get these crazy, like, cool geometric results. Anyway, that's sort of what I do, but we're going to generalize even more now. Okay, so imagine that you have this wild and crazy two-dimensional, hilly, bumpy surface that the straight lines aren't straight at all. They're not like curves, like they're just wild, crazy things. And now imagine that you're allowed to stretch and shrink however much you want anywhere. So like imagine that it was made of rubber and you just put a whole bunch of pins underneath it and you just start pulling in various directions. When you do that, now we're talking about conformal geometry. So conformal in this setting basically means rescaling. So you're allowed to rescale we're not just talking about like zooming in, zooming out. We're talking about rescaling any individual patch in arbitrary amount. And so while you can talk about so-called invariance in the Riemannian setting, in Riemannian geometry, an example of that would be the product of these curvatures. That's an invariant. It doesn't change, right?
Right.
And so, when we're talking about geometry and invariance, we're talking about things that don't change regardless of kind of like your perspective.
Yes.
We can also ask questions about, well, okay, what quantities in this wild and crazy Riemannian setting stay the same even if you stretch it in random ways. And so then we can talk about these things would be called conformal invariants. So these are things that they're so rigid, they're so invariant that it doesn't even matter how you stretch the thing, they stay the same. And that, like, in a two-dimensional perspective, there's actually not a whole lot of these. It turns out that conformal geometry in 2 dimensions is vastly different from conformal geometry in any number of dimensions more than 2. So like 3-dimensional conformal geometry is kind of like the bottom of where we start, because in 2 dimensions, it's, I mean, for those of you who like jargon, the 2-dimensional conformal group is infinite dimensional, whereas the conformal group in any dimension other than 2 is not infinite dimensional, it's finite. So the geometry is just very, very different. So, but nonetheless, we can talk about invariance on these things. And an example that I would give would be like, how twisty is it, right? So like you could measure the amount of twistiness, and stretching it isn't going to make it more or less twisty, because you're not allowed to twist. You're just allowed to like stretch, right? So twistiness would be something that would be captured as like this sort of conformal invariant. And by the way, there is a, well, I don't know how useful this is for your audience, but there's something called the Weil tensor, named after Hermann Weil, W-E-Y-L. He was a German guy, so you have to pronounce the W as a V. But the Weil tensor is like it's like the prototypical example of a conformal invariant, and it basically captures, and it's used in general relativity too, it basically captures all of the curvature that spacetime has in the absence of matter.
I see.
So if we're talking about gravitational waves, because you don't need matter for gravitational waves to work, the Weil tensor characterizes them. Not because and it turns out that gravitational waves are so-called they're conformally invariant solutions to the Einstein field equations. So here's the link to physics, by the way. You can do like all of this stuff, all of these invariants, they show up in general relativity a lot. Right. So the next thing to do is, I've been talking about 2-dimensional conformal geometry. Well, I mean, we can think of 3-dimensional things. It's a little bit trickier, because what do the bumps look like in 3 dimensions? They're like clumps of higher density space or clumps of lower density space, which is very weird to visualize.
Yeah.
Or we could just go to 4 dimensions, 5 dimensions, 6 dimensions, just forget about visualizing it, and then just use analogies to 2 dimensions and 3 dimensions to think about these things. And so this is where conformal geometry really shines. There's like a long history dating back to the 60s of like studying conformal invariants, and these things show up in physics. There's things called like conformal gravity, which is like a variation of Einstein's field equations, which is kind of scale invariant. So there's a lot of rich structure here, where you can just talk about like what things stay the same and what things don't when you're allowed to stretch and shrink these wild, crazy geometries in higher dimensions. And so what I do, one of the things that I've been spending a lot of time on, are things called hypersurfaces and submanifolds. Now, a hypersurface is an example of a submanifold, but it's probably the easiest example. So a surface is a 2-dimensional thing, right? 2-dimensional thing lives in 3 dimensions. You have like a piece of paper, it's a surface in 3 dimensions. That's a hypersurface. It's just a regular surface too. A hypersurface is just anything where you have like something that is where you have one thing that is 1 dimension lower than the thing that it lives in. So if you have a 4-dimensional thing living in a 5-dimensional thing, then that would be a hypersurface. A submanifold is just kind of the generalization of that. It's just you have a lower dimensional thing living in a higher dimensional thing. So a hypersurface is like the hypersurfaces and curves are like the prototypical examples of submanifolds, because they're like the kind of the extremes, right?
Yeah.
And so the things that I did my doctoral work on was on conformal hypersurface invariants. So conformal means you're allowed to stretch and shrink things. Hypersurface means that these are properties of the thing that lives in the higher dimensional space, not the higher dimensional space itself. And invariant means that these are properties of that lower dimensional thing that don't change when you rescale it. So I developed kind of, I didn't develop a theory of, but I kind of expanded upon and the theory of these things. So the example that I often give is, imagine that you had a sheet of rubber, right? You can stretch it however you want. You can even put bumps in it if you want, make it wild and crazy. Draw with a Sharpie on it, you just draw like a loop. A loop is a 1-dimensional thing. You can only travel in one direction along it, right?
Yep.
So it's 1-dimensional on a 2-dimensional surface, means it's a hypersurface, right?
Yeah.
It's just a very boring one, but it's a hypersurface. And so you could ask questions: what properties of the loop stay the same when you're stretching and shrinking and all these wild and crazy things? Well, the most prototypical example is, how many crossings does it have? Does it cross itself ever? because that doesn't change whether you stretch or shrink it, right?
Mm.
Either it's a complete loop, or maybe it's a figure eight, or maybe it's like a triple figure eight or whatever, but the number of crossings will never change regardless of how you stretch it. And
Right.
so that would be a conformal hypersurface invariant. And whether the loop is open or closed. I mean, if it's a loop, it's obviously closed, but maybe it's just like a line that you drew, or maybe it's like a fully closed loop. So these are questions, or this would be an example of something that is unchanging under this whole stretching notion. Now, the analogy breaks down because when we're in one dimension, living in two dimensions, there's really not very much. Just because you could talk about twistiness, but you can't really talk about the twistiness of a one-dimensional thing, of like a loop. It's a little bit, it doesn't really work. Right. But fortunately, and this is true in Riemannian geometry too, there's not a whole lot of invariance in the Riemannian setting, even without stretching and shrinking. But if you go into, say, 2 dimensions in 3 dimensions, like a surface living in 3 dimensions, now you get a lot more, like the pizza example was one. But even in 2 dimensions living in 3 dimensions, there's not a whole lot of stuff in the conformal setting. So what do? You just keep going up until you find something interesting. A lot of my work for my doctoral work was focused on 4-dimensional hypersurfaces living in a 5-dimensional space.
Interesting. Before we dive into that, though, I think it would be good if you would probably explain, dimensions that are greater than 3, because people only think of forward and backward, left and right, and up and down, right? Because yeah. So, do you want to explain like what like a 4th dimension or a 5th dimension would actually be?
Yeah, so it's funny that you say that, because to me these things are just like, oh, you just work in 8 dimensions. I had a conversation with my supervisor the other day, and I'm like, well, let's just work in 39 dimensions and see what happens, right? Like, I just throw that around like it's just an everyday thing, but I often do forget that this is a crazy idea to some people. So the idea is as follows. I mean, if you were a flatlander, there's a great book by someone called Flatland.
Oh, is it Abbott?
Yeah.
Abbott.
I've read that book. Excellent book. If you're a flatlander, you're a creature living in 2 dimensions, right? You only know left and right and forward and backward, right? That's all you know. Like the notion of up and down is completely foreign to you. If you have a brain, which I don't know how that would work if you're a flatlander, but if you had a brain, you would not be able to conceptualize up and down because your brain just isn't developed to conceptualize that. We are, volume landers, if you will. We live in a 3-dimensional world as far as we can tell. Which means, and our brains evolved on the plains of the Serengeti, if you will, or something like that. And it turns out that in order to stay away from lions and to hunt down, I don't know, like elk or whatever, you don't need to do 4-dimensional calculus, right? So our brains, we can visualize very, very efficiently in 3 dimensions, up, down, left, right, and back, forward. But a lot of the rules that we use to understand these things from a mathematical perspective, you can do them in higher dimensions. You just kind of add an extra variable. You just say, well, there's X, Y, Z, and W. Yeah. And you just let that happen. Now, there is no hope of visualizing these things ever, at least not in any sort of useful geometric way. There's a story of one person. I want to say it was Hermann Weyl, who is alleged to have been able to visualize 4-dimensional things. Okay. But this kind of thing is always a story, and this is not something that humans can do. So there is no hope of doing it. Don't try. It is not worth your time. But nonetheless, physics happens in 4 dimensions, right? Physics, as we know it, we have 3 spatial dimensions, and then we have time. Yep. And so if you want to think about, like when you're doing calculations or whatever, you can't draw a movie. You can't just draw a movie. You draw a picture. So you still have to work in 4 dimensions, even though you can't visualize it on a piece of paper. So you do your best, and you think about things in a 2-dimensional way, or maybe a 3-dimensional way, and then you just analogize. So these are, like, the 4th dimension of time is, by the way, very, very different from other spatial dimensions. And when I'm talking about working in 4 dimensions and living in a 5th dimension, I'm talking only about spatial dimensions here. And there's nothing to visualize. Arguably, nothing about our physical universe is related to this. Unless you take string theory seriously, I guess, but neither here nor there. 10 dimensions or whatever. But the reason why it's still useful is because we can learn a lot about the way you can kind of treat dimensions as like a parameter. And certain things will happen in certain dimensions, and you sometimes this is something that miraculously happens in quantum field theory, is that if you just treat dimensions as a parameter, you can extract an answer, and then you can take it down to 3 or take it down to 4 if you're working in space-time, without actually having to work in 4 dimensions to begin with. So it is still useful, but yeah, there's no hope. It's just a 4th direction that's perpendicular to all of the other directions. And a 5th dimension is just a 5th one that's perpendicular to all the other 4. But yeah, there's no hope in visualizing it. Which, you'd think, as somebody who spends their days doing geometry, you'd think I'd be able to. Or you'd think that it'd bother me, and it does bother me, but, I'm out of luck.
What is it, the saying that the universe doesn't have an obligation to make sense to you in that manner, so...
In this regard, it does. And the reason for that is because the only reason why we can only think in 3 dimensions is because our universe has 3 dimensions. If our universe was 5-dimensional, like 5 large dimensions, we'd be able to think in 5 dimensions. It'd be very inefficient to run away from 5-dimensional lines if you can only think in 3 dimensions.
Yeah, that would be really interesting.
Wow. In many cases, you're right that the universe is under no obligation to make sense to you. In this case, it definitely is.
Yeah, that's true. We're working with what we got.
Yeah.
It just is what it is.
Our puny 3-dimensional brains, right?
Right. So how does your work tie in with the holographic principle?
Okay.
Because we talked about conformal geometry, we talked about hypersurfaces and submanifolds, but the last thing kind of on the agenda to define would be the holographic principle.
Yeah, and we'll tie it all in. Okay, so first, we're not talking about holograms here. We sort of are, but we're not talking about like pieces of glass with images in them that look 3-dimensional. Except we kind of are. I'll explain why. So there's this there's kind of 2 holographic principles. There's the one that mathematicians use and the one that physicists use. And it turns out they're basically the same thing. But if you ask a mathematician, they'll give you a completely different answer than a physicist. So I'm going to tell you what both are.
Oh, interesting.
Yeah, so to a mathematician, the holographic principle is kind of like an obvious thing. Namely that the example here is, imagine that you had a drum, like a wire drum, right? You just have a piece of wire, and then you have like a skin or like plastic stretched over it, and it'll make a sound, right?
Mm-hmm.
And so the holographic principle basically is a statement that the boundary of your drum, the shape of the wire, tells you about what's happening on the inside, tells you about the shape of the stuff on the inside. And this basically just follows from like some differential equations. The drum is going to be like it's like an energy minimizing surface, and so it takes on a particular shape that depends on the shape of the drum. And so there's this question of, can you hear the shape of a drum? It's like a beautiful question that popped up in a Scientific American at some point, 50 years ago, which is basically, if you bang a drum and you know what sound it makes, can you figure out what shape it is? Turns out that with few exceptions, the answer is actually yes. And so in some sense, in a mathematical sense, there is a duality between the inside of something and its boundary. So in the case of a drum, it's a 1-dimensional thing. It's like a wire. And you have the inside is 2-dimensional. And there's this dual relationship. So a physicist would just say, look, the holographic principle is learning about the shape of your boundary from knowing about what's happening on the inside. Sorry, that's what a mathematician would say. Is that what I said?
Yes, so you said the opposite, but...
Yeah. So a physicist would say almost the same thing, except they'd say that it's not just that you can learn about them, but that they're actually the same thing. Yeah. So the idea is that when you talk about physics, you might think that it's about exactly modeling reality, but it's not, right? It's about coming up with a system that gives you the right answers for a set of inputs, right? Physics is all about making predictions about the universe. So if you have a system that looks like it's, it looks like it's a race car, but if you plug in the numbers right, it gives you the answer for a rocket ship. Well, you've done physics. You have a machine that predicts how rocket ships behave. It just happens to look like a race car, even though it might not be a race car, right? When we say that we can a physicist will say something like, if you have a system that is mathematically identical, or rather captures the same information on its boundary as you have in the interior, then those two systems are actually the same system. They're describing the same thing. And so they're just dual to each other. And the classic example is the so-called ADS-CFT correspondence. Now, this is a big deal. It was originally conjectured in '95 by Juan Maldacena. Really huge, the guy, he was just like I don't want to say he was a nobody, but he was a string theorist. And then he wrote this paper in 95, and now it has 10,000 citations, which for the record is like it's probably one of the most cited papers in physics at this point.
Yeah.
If only because, it's a lifeline for string theory, if you will. It's one of the things that's made string theory still relevant. So
yeah, isn't ADS CFT kind of based on the one, I guess, not really issue? It's not an issue, but maybe like for surface level interests, it's an issue where ADS CFT arises on assumptions that don't really correspond with the way that we see the behavior of our universe.
Oh yeah, 100%. No, it doesn't at all. But the point is that it's an insight, right?
Right. So, exactly.
So the idea of the ADS CFT correspondence is that there's this thing in general relativity called ADS. It stands for anti-de Sitter. It's a type of spacetime. It's a negatively curved spacetime. So think of it like the spacetime equivalent of a Pringles chip. And it has a certain property. Namely, you can kind of think of this ADS space as like, in a certain sense, as kind of like the inside of a soup can. Like that's kind of how it's shaped. Like that's its structure. Now, like, the way you measure distances is obviously different, but like it has the structure of a soup can. And so you can do normal gravity things inside of this ADS spacetime. You can put black holes down. You can, you can ask like what happens, what trajectories do particles travel in? Fine. You just have a normal theory of gravity. And in particular, you can do string theory there too. You can look at like and string theory famously has gravity built in. So you can do string theory in ADS, and then you can look at the classical limit, and you just get regular Einsteinian relativity in the inside of the soup can. Now, what makes the ADS CFT correspondence interesting is that the boundary of the soup can that's the CFT side. So you have ADS on the inside, and then you have the boundary, which is the metal
field theory.
Conformal field theory. And this is why conformal geometry is relevant, right? So conformal field theory is a type of quantum field theory, which has certain properties, namely it's conformally invariant, so which heavily restricts the type of quantum fields you can have. But it is kind of like a prototype for a quantum field theory. Quantum field theories are generally much more rich. Well, I shouldn't say that. They're less nice, I should say.
Or rigorous.
No, well, it's not that they're less rigorous. They can be much worsely behaved. Just because they don't have this additional constraint of having to be like completely invariant under rescaling.
I see.
But the point is that you can basically do quantum field theory on the boundary of the soup can. And what Juan Maldacena noticed is that you can describe gravitational spacetimes in terms of a field theory on the boundary. So any calculation that you wanted to do, if you wanted to calculate the angular momentum of a black hole in your ADS spacetime, you could do that. You could just run through the calculations and do your general relativity calculation and, plug in the numbers, do your differential geometry, whatever. Or if you're clever, you can go do a calculation completely forgetting about gravity, completely forgetting about any geometry at all, and just do a quantum field theory calculation, and you get the same answer.
Yeah.
And so there's like a dictionary between the quantum stuff on the one hand and the gravity on the other hand. And people love this because it's the closest thing we have to quantum gravity.
Yeah.
Right? Yeah. So what physicists will say is like, look, these two things describe the same system. You can describe the quantum field theory using gravity or gravity using the quantum field theory. So in a sense, they're the same thing. And so when physicists talk about the holographic principle, or really, I'm saying they, like I'm not one of them, but I do this too. We will say, look, these actually describe the same thing. The boundary is the interior. They're just different representations of the same thing. And so this holographic principle is like, and the way it relates to a hologram is that a two-dimensional hologram, like a piece of glass that looks like it has an image, it has extra information. It is a two-dimensional surface, but it contains all of the information of a three-dimensional object. And so in that sense, you're encoding, just like in the soup can, you're encoding all of the information of your 3D thing on a 2D surface, just like how you're encoding all of the information of the inside of your soup can on its boundary. And so this notion of holography is remarkably handy, and people have written papers about it, hundreds, thousands of papers even, because it's tantalizingly close to quantum gravity.
Oh, interesting. Maybe this is my misinterpretation, but I thought that maybe there was a slight difference between the holographic principle and holography, where whenever you're encoding this, say this like laser image into this this sheet, it's technically not a two-dimensional surface because there's a way that you can entrap data in 3 dimensions within, say that film that you want to create a projection for.
Yes. So the way a hologram works, like a glass hologram, right, is you basically have a substance that not only captures the brightness, like the amount of photons that hit it, but also captures the phase information. So you basically have an additional degree of freedom. So even though you only have brightness in a 2-dimensional grid, you have more than just brightness. You also have phase information. And so it's very much the same thing in the holographic principle, right? You have, you don't just have like mass, but you have like quantum entanglement, and you have extra degrees of freedom that are captured in the quantum side that aren't in the gravity side. So there's enough freedom in the quantum side to encode the information about gravity, and vice versa. So it is really analogous, hence the name. It's just a lot more complicated.
Yeah, understood. And maybe to kind of add some really interesting information to this, the holographic principle also, we touched on how it deals with black holes, and black holes. There's that wonderful paradox called the information paradox, where if you have something, a 3-dimensional object that falls past the event horizon, there's the issue of, okay, it's supposed to, based on its point of view, go into the singularity. But then there's the problem of, okay, if we have this notion of Hawking radiation, what happens with its information? Where does it go? Does it disappear? It can't. So the holographic principle essentially gives rise to the idea that the information is coded on the outside of the black hole. It's the surface of the black hole rather than, in tandem with it also being included inside the volume, it is also encoded on the outside. So it gives a potential solution to it.
Yeah, and in fact, it's interesting you bring that up, because that was one of the reasons that motivated holography.
Yeah.
I think in the 70s, maybe it was the 70s, Jacob Bekenstein, or
That's
Bekenstein,
right. Bekenstein.
He came up with this formula that told you the entropy of a black hole. Now, entropy we think of as being disorder, but it can be used to describe more. I mean, you can talk about entropy of a black hole. It does make sense. And it was just this remarkably weird result that it was basically the surface area of the black hole divided by 4 with the right units, which is strange, because you'd think that, like, if entropy tells you how much disorder there is, you'd think it'd be related to the volume, but it wasn't. It was related to the surface area. And that result suggested something special. That the information about a black hole wasn't about what was happening inside. It was about what happened on the surface of its event horizon. And this like, it's named Bekenstein-Hawking entropy formula, because Hawking then later proved it after Bekenstein kind of suggested it. And
using a workaround in quantum from
I mean there's a reason Hawking is so famous, right? The man was brilliant. And one of the like great victories of this holographic principle, this ADS-CFT correspondence, is that it reproduces the Bekenstein-Hawking bound, or the Bekenstein-Hawking entropy formula for a black hole. In fact, the claim is that if you have a quantum system on the boundary of your soup can, you can measure the entropy of a quantum system. It's called entanglement entropy. It basically tells you how entangled 2 things are. And it turns out that if you have a quantum system on the boundary of your soup can, the entanglement entropy of that system is exactly related to the surface area of something called a minimal surface. So think of this like as the sheet of the drum. It's like the thing that takes the right surface shape. And it turns out that when you have a quantum system that is dual to a black hole, the minimal surface that you take the surface area of is the event horizon. And so it's like this wonderful, like, wonderfully brilliant. It's not even a coincidence. It was like it couldn't have been a coincidence, right? Like, it had to work, but it did. And so it's just like, I mean, I think that result it's called the Ryo-Takeyanagi formula. Came out in 2004. People have been working on it for a long time ever since. And that like the fact that you can relate entanglement to surface area is wild, but you can, and it just works.
Yeah. Have you heard about and I'm not crediting only Sean Carroll, but Sean Carroll and a few others are working on something quite similar in terms of quantum field theory, where they're looking at the surface area with relation to the entropy of the quantum, like of a quantum field. Have you heard about that? I mean,
Yeah, I
it's
mean
quite similar.
it is the same thing basically.
Yeah. No, it actually is. That's right.
Yep, it's the same thing. And actually, that particular relationship, that there's a relationship between the surface area of a minimal surface
Mhm.
and entropy on the boundary, is basically the motivation for a lot of the work that I do.
Okay.
I don't know if now's a good time to transition or not, but
We might as well. How about this?
Sure.
Whenever we come back, we will talk about that in segment 3.
all right,
Okay.
sounds good.
All right. We'll be back. All right. This is segment 3. It's the last one that we have planned out for you guys. I hope you've been keeping up with everything. I think, Blitz has been doing a wonderful job in terms of making everything very, very layman. You've definitely stuck to the whole 80-20 principle that I said like way back when
Yep.
we first met. So kudos to you, man. So, we ended the last segment talking about how we want to now explain how this ties into Blitz's actual research. So, Blitz, please take it away. Sorry, we kind of did like a weird cutoff there at the end, but for purposes of advertisements.
Of course. Right. So I mentioned that. So I do conformal geometry work, and I work with hypersurfaces. That's at least what I spent a lot of my doctoral time doing. I'm branching out now, but we'll see. And I also mentioned this ADS CFT thing, right?
Mm-hmm.
Holography. That you have a soup can, its edge, its boundary, is conformally. It's like a conformal field theory. It has like some stretchiness to it, and then you have gravity, some sort of geometry in the middle. So the boundary of the soup can is a hypersurface, right? The boundary of the soup can is one dimension lower than the inside, because you have like all the directions that you could go on the inside, but you can't go inward when you're on the boundary.
Mm-hmm.
So we have and furthermore, okay, I have to go into a little bit of technical detail here. The ADS spacetime technically doesn't have a proper boundary, has what's called a conformal boundary. The boundary is infinitely far away, but you can kind of do this rescaling business, and you can get it to be finitely far away. Okay. And so when we're talking about the soup can, we're really talking about the like a conformally rescaled ADS spacetime. But the point is once you're allowed to do that conformal rescaling, now you can do any conformal rescaling. You can stretch it however you want, so long as you end up with the same boundary of your soup can. So the setting now, and this is like a wonderful setting to work in, is you have what's called a conformal manifold on the inside, and it has a boundary, which is a hypersurface. And the way that boundary is shoved in as if the boundary was wiggly or if it was, whatever, that will tell you stuff about what's happening between the two. That will tell you things about, like what properties the gravitational spacetime has, or what properties the conformal field theory has, and things like that. So one of the things that pops up is there are these notions of so-called extrinsic conformal invariance. So if you handed me a loop of string, just to go back to that analogy, the loop of string has a property on its own, right? It has a property that it's a loop, and maybe its length is its own property. It doesn't change. But like if you take that loop of string and you glue it to a sheet of paper, there will be certain properties, like how curvy it is, that will depend on how you glued it in. Mm-hmm. And so we have intrinsic invariance. These are things that don't care about how the thing was glued in, like how many loops it has, or how long it is, things like that. Then there are properties that are called extrinsic invariance. Now, when you take a boundary, the boundary is going to have some intrinsic invariance. It'll have some of its own geometry that's just kind of there, but it'll also have invariants that tell you how it is attached to the edge of your soup can. So when we're talking about the invariance of this boundary of the soup can, or the invariance of this conformal manifold with boundary, we can really talk about what the conformal field theory is doing, like how it actually is relating to the stuff on the inside. So let me just back up and say that there is this wonderful, wonderful thing called renormalized volume. Now, it sounds like a very strange thing to say. You can just think of it as regular volume, like it's an amount of volume, amount of space. But what renormalized means is you just take it, but renormalized volume means that the volume is actually infinity. So you just throw away the infinity part and you get something that's not infinity anymore. And it sounds wild, but I promise you that there's a good way to do this. Now remember, in our soup can, you're allowed to stretch and shrink it, which means that the volume in principle should change as you stretch and shrink it, right? And the reason the volume is infinity is because if it's like the unstretched version, you could go infinitely far and you would never reach the edge, right? That's why it's infinite formally. But it turns out if you do this renormalization procedure where you renormalize the volume, you throw away the infinity part, the thing that you're left with actually doesn't change regardless of how you stretch and shrink it, which is miraculous. And an even better thing than that is that you can actually, in certain settings, you can actually calculate it by thinking about how the boundary is wiggly on, or how the edge of the soup can as a boundary is wiggly, the extrinsic invariance. So here's holography happening again. You have like a property, a global property of the spacetime, this renormalized volume. It's a conformal invariant. You can calculate it just from boundary considerations. You don't even, you basically look at the boundary and you look at what it's doing near the boundary, but you don't have to go all the way to the inside. But the inside has, like, it has volume, so you'd think that you'd have to consider it, but you don't have to. You only have to consider the edge, basically. There's another great example. So that is one of the prototypical examples of holography that happens. Another example, though, is the surface area of like a minimal surface, right? That's also infinite, by the way. Especially, so you want to think of, you have, let's say half of a sphere. You cut a sphere in half. You take half that sphere and you glue it to the inside of your soup can, right?
Okay.
So that might be a minimal surface. Maybe it's not, but let's just assume for a moment that it is. Minimal surface is a technical meaning here, but don't worry about it. The distance between any point not at the edge and the edge is infinity, right? Like that's like we kind of shoved that under the rug, but the boundary is infinitely far away. So if you're going away from the boundary, then you're going infinitely far away. So the surface area of this sphere is formally, it's infinity. But again, we can throw away the infinite part and just get some nice number. And it turns out that that nice number, the non-infinite piece, that's the entropy of the boundary state.
Oh.
And so, yeah. So it's actually the renormalized area of the surface, not the actual total area. Especially if your boundary is so-called anchor, or if your surface is anchored to the boundary, which is like when it's glued to the edge, right?
Yeah.
But and so there are a whole bunch of these invariants of the interior of the spacetime that you can actually just calculate by doing stuff along the boundary. And so a lot of my doctoral work was computing generalizations of these conformal invariants. And so it's useful, right? Because depending on the situation, sometimes it's easier to calculate something in a gravitational setting than it is to calculate in the conformal setting. So if I can give you a tool that just means you just take the geometry. You don't have to do any quantum mechanics or anything. You just take the geometry, which involves a wiggly boundary, which involves complicated geometry. But you just take the geometry and you do a calculation. That thing that spits out is a number in the quantum field theory that you were interested in. Maybe it's the amount of entanglement you have. Maybe it's the so-called Weyl anomaly, which is a separate thing. It tells you it's a whole thing, but I'm not going to get into it. So we're talking about the invariance of hypersurfaces living inside of a conformal manifold, and that's what I do. I study these things because it turns out that they have huge applications. They have applications to highly theoretical physics. I like to think I still have a bit of physicist in me, but I think a lot like a mathematician. Because when the reason I say that is because really, when we're talking about what happens in the interior of the soup can, we're talking about something that solves the Einstein field equations, usually. It's because that's what space-time does, right? Space-time solves the Einstein field equations.
Yeah.
But like, what if it didn't? What if there's just some other type of space-time? An example of such a thing would be constant scalar curvature. Not going to go into the details of what it is. It's a weaker version. It's a more general type of space-time than a space-time that satisfies the Einstein equations. But we can do the same game. We can just say, well, what if instead of having Einsteinian gravity, you have this other thing? Can you do holography on that? It turns out you can. And you can do the calculations. And so what I spent my time doing, and by the way, the reason why this is interesting is because once your interior geometry is allowed to be more general, you get a lot more freedom of the kinds of invariant things along the boundary. like just so much more. So it was interesting to generalize. And so what we found is, and like this was kind of like the big theorem of my doctoral work, basically, is you have all of these invariants. So we kind of have to back up again to the Riemannian setting of a surface in 3 dimensions just to explain what this is about. But there's basically, imagine that you have a surface in 3 dimensions, right? It's wiggly, wobbly, whatever. It's just like a surface, not stretchy. It's just a normal thing. You can imagine drawing an arrow on the surface that points out from the surface at every point, right? We call that a normal vector. Normal in, I was talking about this with my wife the other day. Normal has like 180 definitions in math, and they're all completely unrelated. This version of normal means perpendicular to or orthogonal to, meaning it just sticks out from the surface. So you can imagine that you have this wibbly wobbly surface, and you have this vector, this arrow that just sticks out, and depending on how it wibbles, the vector moves around, right? And so there's this thing called the second fundamental form. It's a great name that tells you basically how does the arrow change directions as you move along your surface. It turns out that that is something that's called a Riemannian invariant, which means like even if you describe your surface using different coordinates or whatever, it's still the same thing. It turns out that if you throw away a particular bad piece of that, it's also a conformal invariant, actually. If you throw away the piece that is the average motion, so you can imagine moving and you're on a surface, you can imagine moving in each of the 2 directions.
Yeah.
You could kind of average the motion in both those 2 directions. If you throw away that piece, the thing that's left over is conformally invariant. It's called the trace-free part. If you took linear algebra, I guess, the trace of a matrix is like the sum along the diagonals. So you throw away the sum along the diagonals and you get the trace-free part. So the trace-free second fundamental form is conformally invariant. And this is convenient. And it basically, it is one of 2 conformal invariants that describes a surface in a flat 3-dimensional space. So when I say flat, I just mean like a regular Euclidean space. But if your Euclidean space isn't 3-dimensional, or sorry, if your 3-dimensional space isn't Euclidean, meaning that it's wibbly wobbly, and then you shove this surface in there and then ask how the normal vector moves, there's a lot more that can happen. You can have a lot more of these so-called conformal fundamental forms, which generalize the second fundamental form, the trace-free second fundamental form. And these things basically tell you kind of like at higher level of detail how the normal vector moves around. They basically ask, okay, if you took your surface and you kind of like stacked a whole bunch of them on top of each other in like both directions, and then you put normal vectors on all of those, how would those move relative to the ones on the original surface? Because maybe like they would have to get smaller or get bigger as you stack them. Maybe like you can imagine stacking spheres on top of each other, the spheres get bigger.
Yeah.
So the so-called higher conformal fundamental forms tell you how the vectors move as you kind of get further and further away from the original surface. Anyway, that was a bit of a tangent, but one of the things that you can do is you can do this in exactly the conformal setting. You take your hypersurface, which is just like a regular surface. It has a vector that points off of it, an arrow. And you can ask, how does it wiggle around as you move around your hypersurface? And then you could ask, well, what if you, so the word is foliate. What if you stack your hypersurfaces on top of each other? And then you ask how the vector moves along those. And so you can get these conformal fundamental forms for hypersurfaces in a conformal manifold, which is the setting of this ADS-CFT business. Except we're not working in ADS anymore, as I mentioned. We're working in this more general spacetime.
Yeah.
It's constant scalar curvature spacetime. By the way, just as an aside, I don't work with time ever. I only work in like spatial directions because because it's really, really messy. Once you throw in time-like things, it's very, very bad.
I could imagine.
I am actually working on a project that's involving that, and it's so much worse. But anyway, So one of the things that we found is that, so when you're doing this business of conformal fundamental forms, it turns out that you can only make so many of them. You get your trace-free second fundamental form for free. That one's always there. And as you go higher and higher dimensions, you eventually run into a roadblock. So if you're in, say, 80 dimensions, you have an 80-dimensional conformal manifold, and you have a 79-dimensional hypersurface living in it, you could get roughly 40 of these. It's roughly half of the dimension. It's like half plus like 2 or something like that, right? Oh. It's annoying, is what it is. And so and it was like the subject of months of struggle as to why this is the case, and we actually still don't even know if this is provably true, but we couldn't come up with a way to build the higher ones. And and the other half, you can keep going up to all the way up. So you can never really go higher than the dimensions. So you can never really get like an 80th fundamental form in 80 dimensions, but you can go up to there so long as the earlier ones are 0. When I say they're 0, I mean like imagine the second fundamental form tells you how the vector moves as you move around on the surface. If it doesn't move around, if it doesn't change directions, then that thing is 0, right? So if the first half are 0, then you can make the second half. Kind of weird, but you can do it. And what we found is that if your space-time, or if your space, I should be saying space, not space-time, but I'm going to keep saying space-time. If your space-time has all of these conformal fundamental forms, 2 through d minus 1, because that's the highest you can go, d being the dimension. If they're all 0, turns out you get Einstein space-time again. So these are what you might call obstructions. That if you have any of these things that aren't 0, your soup cannot be a solution to the Einstein field equations. But if they are all 0, then it automatically is a solution to the Einstein field equations, which is kind of remarkable, and at least to me was very, very surprising. And it is probably the only reason I got a postdoc.
Wow, that's awesome.
Yeah. So it basically and the setting here that we're talking about is something called a Poincare Einstein manifold. Poincare is the reason it's called Poincare and not just Einstein is because it has like this extra property that it's like infinitely large, but you can kind of rescale it down to make it like finite. And so this is like these so-called Poincare Einstein manifolds are like very highly studied. Like they're like a big deal because I mean they are everything in the ADS-CFT correspondence. That's all people are talking about. So if you can give a condition, no, I'm just tooting my own horn. If you can give a condition that tells you the properties of the boundary, that it has to have certain properties in order for that thing to be a Poincare Einstein manifold. Well, that's just great. So that was something nifty. I mean, at least I thought. And I got these conformal fundamental forms that are they're my baby. And I spent 4 years developing them with my thesis advisor. And so when all you have is a hammer, everything looks like a nail. So now all of the projects that I'm working on, I'm like, how can I make these? How can I fit these into this project? How can I make these solve my problems? Because it turns out that these solve the problems in this other case. It actually turns out that a problem I'm working on right now is, can you build the Deith as in D apostrophe TH? Like in 80 dimensions, can you build an 80th fundamental form? You can certainly build 79. Can you build an 80th? Turns out the answer is yes, sometimes. And maybe this is the appropriate time to segue, right?
Yes.
So here's the weird thing, and this is still fundamentally mysterious to me, is all of these caveats I've said about sometimes have to do with whether the dimension that you live in is even or odd.
That's
which
interesting.
It's so weird, right? So these fundamental forms that I built, right? In odd dimensions, you can never build more than the bottom half, unless they're all 0. Then you can build the top half. Half being rough, right? You get the bottom half. They're relatively straightforward to build. I should probably work on proving this at some point, but I don't think that it's ever possible to build the top half. In even dimensions, you can always build all the way up to d minus 1, always. This is actually a paper that I just published, just got the proofs for, and just sent them back to yesterday. Actually, no, that was yesterday. You can always build these things. And furthermore, whether or not you can find the next one higher, the 80th one in 80 dimensions, for example, you can so if all of the lower ones are 0, you can always build that one in even dimensions. You can't do that in odd dimensions. In odd dimensions, even if all of the lower ones are 0, you need an even stronger restriction to make to build the 80th one in this example. And the only reason why this happens, as far as I know, is basically you have I don't know if anybody remembers this from calculus, if you took it, but you have a Taylor series, and the Taylor series only has even terms in its expansion. So you have like a term that's like 1 plus a number times x squared plus a number times x to the 4th plus a number times x to the 6th and so on. And it turns out that at a certain order in your expansion, you run into a problem. And if you're even dimensional, that you just narrowly avoid it. And if you're odd dimensional, you run into it. So, and like, there's just like this mysterious thing that happens. I mentioned this thing about renormalized volume earlier.
Yeah.
It's actually only conformally invariant in even dimensions. In odd dimensions, it's not, which is weird. Also, in even dimensions tend to be better, by the way, for whatever reason that I don't understand. Well, I have an inkling, but also in even dimensions, there's another invariant. It's just another number that tells you about the geometry called the Q curvature. And there is a formula for the renormalized volume in terms of the Q curvature when you're even dimensional. There is no such thing when you're odd dimensional. And so there's just this, and I don't understand this at all. There's just this strange specialness of being even dimensional versus odd dimensional. And even in my more recent work, where I'm working on submanifolds, not just hypersurfaces, you get like these weird things happening. Like I just found out about like I gave a talk on this on Friday. I just found out about this literally on Friday. There's this very strange thing that happens that if you have a 3-dimensional thing living in a 10-dimensional space, you get a special invariant. It's not if you have 3 and 11, 2 and 10, 3 and 9, it's not invariant, except if you're in 3 and 10. So like there's this very, very strange like specialness about various dimensions, which points at something really deep. And I don't know what it is.
That's interesting. And in giving this talk, was there anybody that was like on board with like, yeah, I've seen this, or
Actually,
yeah. Oh, really? Okay.
Yeah, actually. And so tell you a funny story. So after the talk, somebody said, hey, have you looked into Ramanujan's papers? If you don't know who Ramanujan is, do you know who Ramanujan is?
No.
He was a mathematician in the early 1900s. He was an Indian fellow, completely self-trained. Like he didn't have any formal schooling at all. Yeah, but he's worthy of a podcast all on his own. He was a number theorist primarily, and he basically claimed to come up with these formulas that he came up with in his dreams, like that God told them to him in his dreams.
Okay.
And at first, like he was an Indian guy, and he wrote letters to people in England to try to convince them to look at his work. They didn't take it seriously.
I've heard of this guy.
Yeah. This guy was completely crazy. Not in like a bad way, like brilliant, like probably a savant, like one of those where like he doesn't know how he came up with the answer, but he just does. Anyway, so he has like thousands of pages of notes that aren't really published, but you can go look through them of just like things. And somebody, I guess, was looking through those, 15 years ago, and discovered there's some stuff in some quantum stuff that shows up in there. And somebody like some stuff that's related to quantum physics, and this paper was about 3-dimensional submanifolds of 10-dimensional volumes. And so somebody mentions, hey, at the end of my talk, somebody mentions, hey, those coefficients, because it's when one of these coefficients is 0, is when something special happens, and it's 0 when you have 3-dimensional thing and a 10-dimensional thing. He said, those coefficients look really familiar. Have you checked out Ramanujan's notes before? I'm like, no, tell me about it. So he told me about it. And I'm like, yeah, I'm going to spend the rest of the, it was like a 2-day seminar, 6 talks the first day, 5 talks the second day, like 7 hours and 6 hours of talks. It's pretty intense. But I spent the entire rest of Friday working on my computer, trying to calculate these things to see if this happens elsewhere. And then I just stayed home and I skipped the rest of the seminar on Saturday just to work on this on Saturday, because it was the weirdest connection. And I happen to have a friend who's a number theorist who works with, he's actually a TikToker too, who works with so-called modular forms and elliptic curves, which are exactly the kinds of things that might show up in these coefficients. So yes, this kind of thing happens where these special dimensions might have something to do with number theory and elliptic curves, and quantum field theory somehow are coming in. So there's hope that there might be some really deep connections there. I don't want to say that there'll be anything huge, but who knows?
No, I think that's, first of all, I think that's fantastic. Like, that's really interesting. And secondly, I think that is actually where we should end this, because that is a awesome mystery. And I obviously I hope that there's, for your sake, that is something quite profound, hopefully. But
Me too.
Man, that's a really cool. That's really cool. I love that. And hopefully, sorry, what was his name?
Ramanujan.
Ramanujan. That would be really interesting if there was a tie there.
Yeah, it wouldn't be the first time that Ramanujan's work came up in physics.
Nope.
Or anywhere else.
That's for fact. Well, Blitz, I got to say, this has been wonderful. I'm really happy that you were on the podcast and were able to give deeper insight into mathematics and physics and just like some really cool history in between those subjects. And it was fantastic. Thank you for being on the podcast.
Thank you for having me.
That is all for this episode of Everything STEAM. I just want to take a quick second and thank Blitz for sharing his knowledge and expertise about mathematics, physics, and science history. If you want to connect and see more of his content, I recommend that you search Dr. Blitz on TikTok. I would also love to mention my amazing team for their collective efforts to make this show happen. This podcast was edited by Ariel Piermont, QC by Panupit Erikset, and the episode art was created by Gabrielle Edmiston. After the episode, please give our podcast a rating and review on whatever platform you get your podcasts on. I know I do state this in every episode, but the feedback is absolutely necessary, and it will help us out in the fight against the algorithms. Lastly, be sure to check us out on all the socials for podcast news, upcoming episodes, and just fun STEAM content. Just search Everything STEAM on Threads, Instagram, TikTok, and Facebook to join in on the fun. Once again, thank you for listening to Everything STEAM. I'm your host, Sam Stanford, and as always, stay curious.